2,000 kilometers above Earth, in an orbit almost nothing else uses, a satellite is taking constant fire. Protons at nearly the speed of light, trapped in Earth's own radiation belt, pour through it on every pass. If that satellite is what most satellites are, aluminum, wiring, fuel, almost nothing happens. If it is carrying a thermonuclear weapon, the story changes, because what makes that weapon work is over 100 kilograms of uranium wrapped around its core. A fast proton hitting a uranium nucleus does not bounce off. It shatters the nucleus, and dozens of neutrons spray out. So the question is whether anyone can be close enough to catch them. Areg Danagoulian at MIT's Department of Nuclear Science and Engineering worked out what that would take and published it in Nature in July 2026. A detector the size of a large shoebox, 4 kilometers away, counting for about 7 days. 10 of them cut that to 15 hours. And the inspector sends nothing at the target. No beam, no source, no accusation. Nothing has been built, but no method for checking whether there is a nuclear weapon in orbit had ever been published in the open literature before this. The Outer Space Treaty banned nuclear weapons from orbit in 1967. It has no inspectors. So when American officials said in 2024 that Russia was building a satellite to carry a nuclear weapon on orbit, the claim rested on intelligence, the kind of evidence a government can simply deny. The satellite they meant, Kosmos 2553, sits in a band left almost empty because the radiation there ruins electronics. Russia says it is testing instruments under exactly that radiation. What is inside has never been shown publicly, and the paper borrows only the orbit. That threat is not hypothetical. It has happened once. In July 1962, the United States detonated a 1.4 megaton warhead 400 kilometers over the Pacific. In vacuum, there is no blast wave. What the explosion did was inject something like 10 to the 29th electrons into the inner belt, and Earth's magnetic field kept them there. Satellites did not die in the flash. They died over the following months, dragged back through that artificial belt on every orbit, at least 6 of them, including Telstar 1, which launched the day after the test. So back to the belt, and the idea the paper turns on. Finding hidden nuclear material normally means shining something at it and reading what comes back. And firing a particle beam at another country's satellite is an act, not an observation. What Danagoulian noticed is that the beam is already switched on. Cosmic rays from the galaxy hit the top of the atmosphere and splash neutrons back upward. A few of them decay in flight into protons, and Earth's magnetic field grabs those protons and keeps them. Over millions of years, the inner belt has filled with protons carrying up to 1 billion electron volts, bathing that orbit for free. Now, put a heavy nucleus in that beam. A proton arriving with 1 billion electron volts starts a cascade inside a uranium nucleus, knocking nucleons into other nucleons until what is left is so hot it boils neutrons off. About 44 neutrons out for 1 proton in, from a relation measured on thick uranium targets in the 1970s. Aluminium and the hydrogen-rich plastics of an ordinary spacecraft give back almost nothing. Fold the real proton spectrum along Kosmos 2553's real orbit into that yield, and the modeled weapon throws off up to 34 million neutrons a second, 91 billion of them over 6 hours of flying. And here the problem starts, because the proton flood that creates the signal is what makes it nearly impossible to hear. The detector is a plastic scintillator, and the way plastic sees a neutron is indirect. The neutron hits a hydrogen nucleus. That nucleus is a proton. It recoils, and the moving charged proton makes the plastic flash. So the sensor is functionally a proton detector, sitting inside a storm of 800,000 charged particles per square centimeter every second. The first filter is diamond. Every scintillator pixel, 9 millimeters of plastic, is sandwiched between two 1 millimeter plates of synthetic diamond, one above and one below. A charged particle from the belt has to cross diamond to reach the plastic, and diamond registers it in under 50 picoseconds. A neutron carries no charge and slips through that millimeter of carbon, leaving nothing behind. So the electronics run in anti-coincidence. If the diamond lights up within a nanosecond and a half of the plastic, the event is thrown away. In simulation, every incoming proton was rejected. The cost is that each veto blinds a 13 by 13 block of neighbors, and the array ends up deaf 23% of the time. The second filter answers a harder question. Which direction did the neutron come from? Earth's atmosphere makes neutrons too, splashed upward by the same cosmic rays. So the array is doubled. Two 30 by 30 planes 10 centimeters apart. A neutron scatters in the top plane, leaves part of its energy there, and reaches the bottom plane a measurable instant later. The two hit positions give the angle it turned through. The flight time gives the energy it still had. The energy it dropped up top tells you the angle it should have turned through if it fell from straight overhead. When those two agree, it came from above. In a simulation of 1.68 billion atmospheric neutrons arriving from below, not one got through. Both filters together leave just over 0.5% of the neutrons coming from above. And the source is not steady. The proton flux peaks on particular magnetic shells, so the weapon is loud for a few minutes at a time, several times a day. The inspector has to be underneath it during exactly those minutes. So here is the ledger, and it is startlingly thin. 91 billion neutrons leave the weapon over 6 hours. 4 kilometers out, a detector 30 centimeters on a side covers about 1 part in 2 billion of that expanding sphere. Roughly 40 neutrons actually cross it. 40. 0.5% of those register. The vetoes are blind a quarter of the time. And 6 hours of watching yields about 1/6 of a single count. Run it for 7.2 days, and the expected total is 5. 5 neutrons. And this gets reported wrong, so it is worth being exact. 5 is not the threshold. 5 is the average you expect. When you expect an average of 5, the chance of seeing at least 1 is 99.3%. And 1 is the threshold, because across that same week, the modeled background delivers less than 1/100th of a count. A single neutron of the right energy from the right direction in the right minute is the entire case. Move closer and it collapses fast. 10 CubeSats at 4 kilometers need 15 hours, and those same 10 at 1 kilometer finish in about an hour. 1 pass. Now, the honest read, and it is most of what stands between this and a working inspector. The calculation assumes the weapon is bare. Wrap it in polyethylene, and the neutrons get absorbed on the way out. 20 centimeters cuts the signal to about 3%, and the shoebox has to grow into a detector panel 1.5 meters across. Shielding costs the other side too, since the uranium's own heat then has to escape through an insulating blanket, but that counterargument is a sketch. Then there is specificity. This finds a large mass of heavy elements. It does not identify uranium. Lead spalls, tungsten spalls. A dense shield flown for some ordinary reason, or a decoy put there on purpose, would sound just as loud. And the detector does not exist. Every rejection number here comes out of a simulation. Nobody has irradiated the electronics, run them in vacuum, or synchronized 1,800 pixels to nanosecond precision, somewhere delivering nearly a kilorad a week. Beyond the hardware sits the part physics cannot settle. This means flying an inspector to within 4 kilometers of another state's satellite. The paper's defense of that distance is a list of close passes that already happened without a crisis. That is precedent. It is not consent. What the paper delivers is a physical signature and a scaling law with the analysis code published openly. The next steps are concrete enough to start on now. Build the two planes, put them around a shielded uranium proxy in a laboratory, then fly one and find out whether the real background behaves the way the simulation says. Until then, what changes is what the evidence could look like. Right now, a claim about a nuclear weapon in orbit is one government's word against another's. This version ends with a number, and anyone with the same detector would get the same one.